So, previous video looked at the chemistry that can happen between amino acids, particularly to have the carboxyl group of one amino acid react with the amine group of another amino acid. And that is how we generate, through a condensation reaction, the peptide bond that connects all amino acids together to make our peptides and proteins. On that slide, we also sort of talked about the sulfur chemistry that happens with glutathione. What we're going to do on our next slide here is a two-part slide. We're going to talk about additional peptide chemistry that can happen with side chains, with backbone atoms, with things like that, to highlight the specific chemistry that we see with glutathione. And again, looking at the structure specifically of glutathione. And then we're going to look at how we form the chromophore that we see in green fluorescent protein. So I'm going to start over here first, and I want to sort of look at the structure that we have of glutathione. Now, when we talked about glutathione, we sort of just indicated that it was GSH. That's how we called glutathione, or abbreviated glutathione. And a lot of times we're going to see that we abbreviate things with a letter that maybe tells us what it is, but then importantly, the functional group. We're going to see this with CoA. We often call CoA SH. Okay, so what we're going to see here is that the important functional group that we have in glutathione is that thiol group. And again, two thiols in the reduced form are going to come together. Let's flip back here just to kind of remind ourselves. So we're going to see here that we've got two glutathiones, and that thiol is the reduced form. And when we enter find or encounter an oxidizing species, what happens is we neutralize or oxidize that, or neutralize by reducing that oxidizing species. Glutathione itself becomes reduced, okay, and then that forms that disulfide link. Right? So thiols are the reduced form, disulfide are the oxidized form. So we're just going to take a deeper dive now as to the chemistry that we specifically see with glutathione. We're going to look at the structure that we have for glutathione. So specifically for glutathione, we're going to see that we've got 3 amino acids, so it's essentially a little tripeptide. So I'm going to kind of bracket where we have these amino acids here. Remember, anytime you want to find where we have an amino acid sort of like break between amino acid 1 and amino acid 2, you're going to be looking for a peptide bond, okay? But what we're going to see here is we're going to see a unique kind of bond that we have here. So here's the 3 amino acids that we have here. We're going to have glycine, right, G, and this is the simplest amino acid, right? We're going to have basically just a hydrogen atom that we're going to have as our backbone. I'm going to go ahead and highlight just so that we can see here. Here's the N-C alpha carbonyl, right? That's what we're going to have. And then we have our C terminus here. So this is again where our R group is. Our R group on that alpha carbon for glycine is just a hydrogen. Then here's our important cysteine residue, right? So our cysteine residue, here we're going to have our NC alpha carbonyl, and then we've got our important thiol side chain that we have there. Let me change colors here just so that I can be consistent with what I'm showing here. So side chains we can show in green. So there's our important thiol side chain in that important functional group. Now what we're going to have here with this first amino acid is we have a glutamic acid. So glutamic acid, which we know is E, but watch here, when I identify where the peptide backbone is, NC alpha carbonyl. You'll note here that it's actually the side chain, and remember, for glutamic acid, it's a carboxylic acid for that functional group. It's actually the side chain that participates as the carboxylic acid group to form that peptide bond with the alpha amino group that we have there, or that amino group that we have there in that cysteine amino acid. So really sort of unique chemistry. We call this, it's still a peptide bond, but this is specifically an iso peptide bond. Iso meaning same, so it has the same functional groups. We're going to have a carboxylic acid react with an amine to generate an amide, but it's not truly a peptide bond because we did not use the carboxylate group of the amino acid backbone. Okay, so here again is just the structure that we have. I want you to remember that glutathione is a tripeptide. I importantly want you to remember that the important amino acid that we have there is cysteine. So highlighting again what we saw on that previous slide there, glutathione has the thiol in its reduced form. It encounters, and here again, we're just showing a specific oxidizing species. We're showing molecular oxygen. Molecular oxygen can get reduced to water, but in general, we can really say that it's going to be any oxidizing species. When we want to show an oxidizing species, we're going to show it like that. And again, oxidizing species are reactive They can do damage to biological molecules, and so we are going to reduce them, and whatever that happens to be for that biological molecule. But again, that means that we have essentially neutralized that offending oxidizing species. So what fundamentally happens is we link two of those glutathiones together to form that disulfide linkage. So again, we've got this disulfide linkage. So maybe I'll still use green here to indicate those are the side chains that are connecting together with this disulfide linkage. So we've got this thiol that was reduced, and then we form a disulfide, which is oxidized. So just want to remind ourselves down here, we've got two glutathiones. When they encounter some kind of an oxidizing species, so like I said, I'm actually going to draw it like this so that we can make sure to indicate that this is a redox reaction. So something gets oxidized, something else gets reduced. So this is an oxidizing species that is itself reduced or neutralized. And that happens because we hook those two glutathiones together and form that disulfide link. We're just going to keep this simple. I don't need to draw all that out there. GSSG. Now, here's an important part that we're going to get to later. I'm going to give you a preview of something we're going to see a little bit later on. This is not a one and done sort of molecule. We need to be able to think about how we regenerate glutathione. So remember, glutathione in this form is oxidized. So getting it back into its reduced form, we have to have something else in a reduced form that itself becomes oxidized. I'm going to give you a little preview about what that molecule is. We're going to learn about it later on. It is an important molecule called NADPH, and that is it in its reduced form, and it becomes NADP plus in its oxidized form. So it undergoes redox chemistry, becoming oxidized so that glutathione in its oxidized form can be reduced and thus regenerated. I know, lots of terminology there. So we're going to revisit this later when we learn about how your body makes NADPH and, again, the important things that it's useful for. All right, so that's some chemistry that happens with glutathione. On the right side here, I just want to tell a little interesting story about how we make green fluorescent protein, or how green fluorescent protein actually has its color. So an important thing to highlight here is when you have aromatic amino acids, they have a lambda max, an absorbance maximum, at 280 nanometers, and that's in the ultraviolet region. So again, when we have any of those aromatic amino acids, and hopefully you remember that's going to be tryptophan, tyrosine, phenylalanine, and then tryptophan. We've got tyrosine that we see right here. So when we have something that absorbs in the spectroscopic region, in the electromagnetic spectrum, it's often because it has conjugated double bonds. Remember what we have for DNA, right? DNA has those aromatic bases, and so that's actually going to have an absorbance value close in the ultraviolet region, but at 260. So its lambda max is 260. For proteins, because of those aromatic amino acids, it has a lambda max at 280. Those are two numbers that I want you to remember. But an important concept that we're going to see here is the length of that conjugated system is going to be directly proportional to where it absorbs in the ultramagnetic spectrum, whether it's in the ultraviolet region, whether it's in the visible region of the spectrum, or whether it actually moves into the infrared sort of region. And here's the key. The more extended your conjugated system is, the more you do what's called red shifting. You actually move, in this case, from the ultraviolet region, okay? And when we add or extend that conjugated system, we redshift. We move it to longer wavelengths. Once we go from the ultraviolet region, which is 260 and 280 for DNA and DNA, RNA, and then for proteins, and then we extend that conjugated system, we're going to move into the 400 to 700, 750 sort of range, which is going to be in the visible spectrum. And then if you redshift further, you're going to be in the infrared region. But here's how this chemistry happens, okay? We're going to look down below. Remember, when you're doing things like reaction mechanisms, you want to be able to look and say, is there a new bond that's formed? Okay, and one of the things that we're going to see is if I sort of trace this backbone, I'm going to have NC-alpha carbonyl, NC-alpha carbonyl, NC-alpha carbonyl, and if I come down here, I'm going to have NC-alpha carbonyl Oh, I go NC-alpha carbonyl, NC-alpha carbonyl. What I've created is a new bond with some backbone atoms. So I'm going to highlight here that this is my new bond that I'm making, right? So this bond right here, this is a new bond. So mechanistically, anytime you're looking at a new bond that's being formed, you're looking at one atom acting as a nucleophile and another atom acting as electrophile. So when we look at these two atoms here, unlikely that we're going to see a nitrogen acting as an electrophile. Nitrogens are really good as nucleophiles. Okay, so it's likely that that carbon was an electrophile and this nitrogen was a nucleophile. So if we try to map on and identify, and this is color-coded anyways to sort of help us see this, we're going to have the lone pair of electrons on this nitrogen atom be the nucleophile. And then this carbon over here is going to be our electrophile, right? We know that when we have carbonyl-containing functional groups, that's going to be a great electrophile. So these, again, are the two atoms that we're going to have down here that now are connected together. And so when you draw a mechanism, all you really have to do is draw an arrow that goes from the nucleophile to the electrophile. Now, clearly, there's a little bit more chemistry that happens here because I've got an imine here. Don't worry about that chemistry, but ultimately at the end of the day, what I've done is I took what was a 3 double bond conjugated system and I've extended it to include all of those pi electrons. Okay, so we've extended our conjugated system. So we've extended our conjugated system. Okay, and what that does is it creates a chromophore. A chromophore is just a colored species, and particularly for green fluorescent protein, okay, so green fluorescent protein, what we do is we make this extended conjugated system. We have redshifted so that we move it into the visible spectrum and into the green. So I just want to kind of show that down here just on a little sort of spectrum that we have here. So if we've got the ultraviolet region, and again, that goes till about 400 nanometers. And then from about 400 to 700 nanometers, that's sort of a good range to think about sort of the visible spectrum. So again, this is the visible spectrum. In the ultraviolet here, we've got A2680, and then absorbance at 260 and 280 for our nucleic acids and for our proteins. So again, when we just had that tyrosine residue that we had in green fluorescent protein, it was not going to be in the visible spectrum. But once it does this chemistry that we sort of have shown here, it redshifts. And so this tyrosine is then going to be a modified tyrosine residue, and that ends up moving us into the green portion of the visible spectrum, right? And this process is called red shifting. And just to make sure that you sort of remember, when you're looking at things that are in that 400 region, this is going to be purple color, right? We've got ultraviolet, and then that bleeds into violet, and then all the way at the long wavelength is going to be red, and then over here we're going to have infrared. Okay, so red shifting means moving to increased wavelengths, which again is smaller energy. Okay, so the last thing I just want to give you as a practical example, right? You've probably heard of something like beta carotene, things like that. That's orange, right? What makes carrots orange, melons orange, all that. If you look at the structure of beta carotene, what you'll see is you see a very long extended conjugated system. So conjugated that you actually move it almost to the end of that visible spectrum. Okay, so just a couple of practical examples to think about this concept that we see spectroscopically of red shifting. I want you to know sort of for proteins and then for nucleic acids where we have our absorbance maximum. So lambda max for nucleic acids is 260, and then it's 280 for our proteins. And then a little bit more detail here in terms of the structure that we see of glutathione.